Alright guys, so from last week we learned nodal analysis for the circuits. So this week we'll be going to loop analysis, right? So I hope you all understood everything from last week. So as I said, with the analysis, we have two ways you can analyze it, right? We have nodal, which we did last week, and we have loop analysis. Alright, so nodal is when you're using nodes, and then loop is what obviously you're using loops. Alright, and just like I said, since you have these two now, you always use the one that have the least out. So if you notice in a circuit you have less nodes, you use node analysis. If you're using doing a question, sorry, and you notice have less loops, you use loop analysis. Alright, so just the easier one to use. They both get the same answer, but this one will take way longer to do than the other one. Alright, so I look to get cracking. Wait, why am I using this to use this? A drawing pad. Nice Lego. So as usual, there are steps that you need to follow to do the questions. Alright, so it's similar to nodal in terms of the steps, like the dependent sources, that you need to write the equations for the dependent source. That's not going to change, regardless of what type of analysis you're using, right? So for loop analysis, yeah, these are the steps. So as you will see in the questions I do afterwards, these are the steps you'll normally follow through. Alright, so the first step you label and you draw any loops. Right, you normally name a loop I1 or I2. Alright, so that is normally the consensus, right? And then you have to assume a direction of it. So the loop can either go in a clockwise direction or anti-clockwise direction. The consensus or the norm is to go clockwise, right? But wherever you choose, just keep it constant for all the loops. So there'll be like one loop going clockwise and the next loop going anti-clockwise and you just switch into all the time. Just keep it constant for all the loops, as you'll see. Alright, so that's step. Step two, you have to analyze or look in the circuit for something called a super loop. So just like the super node, this is the opposite, but this for loops. We call it a super loop. Alright, and you will see eventually what this means. So the same thing just like before. So in nodal, you label your nodes, and this one you label your loops. In nodal, you look for super loop, super node, sorry, and in loop, you look for super loops. That's the opposite. Alright, the third step, that's like the nodal, you need to write the equations for the loops, right? So we use something called Kirchhoff's voltage law, which just means that the sum of the voltages in a closed loop must sum to zero. Yeah, that is all it means. You don't write this, but that is what it is. So you're just adding up the voltages across in a loop, and you're just making it equal to zero, just like nodal. But nodal use currents, and this one gonna use voltage. So the equation will look like I plus IR plus IR. For nodal, it was V and R, which will give you currents. But this will give you voltage. That is why it's KVL. Right? The other one was KCL, where the sum of the currents enter in a node must equal to the sum of the current leaving, like KCL. Right? But KVL has to do with the loops and the voltages. Right? And then as usual, you write the equations for the dependent source, just like we've been doing before. So you label your loops, assume the direction for all, you look in the circuit for super loops, because you need to treat that separately. You write your loop equations for each loop, and you write the dependent sources afterwards. That's like, it's similar to nodal, but it just loops you're dealing with now. Alright, so some things to take note of. Anytime current is a current source in a loop, as you see in the questions, that is not shared with any loop. The current in that loop is the current that the current source have in the correct polarity, as you'll see in the question, because you will notice for super loops. Anyway, when you get to that, you'll see. I don't want to give out too much information. Just keep this in the back of your head. Any loop that have a current source, remember current sources look like this, right? That is not shared in between two loops. The equation for that loop would just be the current source value, as you'll see. All right, let's keep it in your mind for now. And the second thing you need to remember, as normal, any voltage drop across a resistor is negative. I think that is known known value from physics and CSEC, right? And any current going in the opposite direction to it will be positive. So for example, if I have this, right, and obviously current I1 going through here, right? The voltage drop across this resistor R1 will be negative. Yeah, everybody remember that from school, right? The voltage will be negative because you're going from a high potential to a low potential. So it'll be negative. All right, you're minus, and from the battery itself. But if you had something like, let me say, you had a battery and you have a resistor. All right, but then you have a next battery here. So if we use any conventional currents, positive, this current here will be I1. Okay, going from positive to negative at the battery, right? So this will go up like this. And this reverse, so plus is here and minus here. So the current will be going through here, we'll name that I2. So if you follow this pattern, I2 will go up here, right? While I1 will go down here. So two things happening here. This resistor have two currents going through it. Not at the same time, it will have a resultant for the two of them in a certain direction, but you'll see that just now. So what you'll notice is if we this current here is I1, clockwise, name this I2. What's happening here? In this resistor here, I1 is the resistor forward. That is, we're dealing with I1 loop, right? I1 loop. This is the loop here. 1, 2, 3. Just keep your eye on that rectangle right there. Don't worry about I2 for now. This is the loop here. Alright, so if we go in through, the current going here, I come down through this resistor and come back up. So since I1 going through that resistor, the voltage drop across it will be negative in the direction that you assume. I assume clockwise here, so going up, that, pow, back to that. So in that direction, if I have a resistor, in that loop right now, the voltage drop across it for I1 will be negative, right? That is I1 there. But now we have I2, and just like the law says, any current that going in the opposite direction to where you assume in the loop, which in this case will be I2, since it's going up here, it will be positive. You will appreciate this more when I do a question, but for now, just remember, if you have two currents going through the same resistor, if I in this loop here, any resistor will have a negative voltage drop for I1, but any current going in the opposite will be positive. Just remember that. For now, just remember it, right? Now do a question, you'll see why it does do that. All right, so super loops. Maybe let's go through this quick. So all our super loopers, as you'll see in the question afterwards, it occurs when you have a current source in between two loops, literally. All right, this happens because you do not know the voltage drop across the current source. Remember, for KVL is the sum of the voltage drops across the components in the loop must sum to 0, right? But you do not know the voltage drop across a current source. You don't know. You don't know. You know the current are coming out of it, but you don't know the voltage drop across it. So when that happens, when you have a current source being shared in between two loops, you then have a super loop. And you need to treat with that separately, right? Just like the super node, right? So to do that, as you see when I do a question, you just join the two loops that the current source connects into one large loop. All right, you're just treating it, you're just not going to the current source, and you're going through the next loop as you see in the question, right? And then as the super node, you had already link equation for it. All right? All right, so let's keep this in mind. The link equation for the super loop, it goes like this. If you have a current source and I1 coming down here and I2 going through here, how does go on this I2 here, right? So the link equation will be real simple. The current not going in the same direction as the current source, subtract the other current source, other current. So this one, I2, going in the same direction as this current source, right? So if I write in the equation, it will be I2, subtract, and the current not going against the current source will be I1. And it will equal to, like we say, the current source was pushing out 3 amps, it will equal to 3. Yeah, and that's how it does. Current that going in the same direction as the current source, subtract the current that going against it, will equal to the current from current source. All right, so that's keep that in mind. While going with subtract against equal to the value for the current source.